So the next thing we're going to cover is related rates, and this is low-key, I think, the hardest part of the unit, so y'all going to have to lock in and pay attention. So before we start, I'm just going to remind y'all that implicit differentiation exists, and what it is if you have like 3y squared plus 6x equals 12y, right? What you're deriving it in terms of affects what the derivative is going to be, right? If you derive it in terms of x, like we've been doing, that's what we're used to doing. Anytime you see a y, you're gonna add a dy dx to it, right? Because it'll be 6y dy dx plus 6, because it's x here, equals 12 dy dx, right? Because we're deriving it in terms of d over dx. We're deriving it in terms of x. If we wanted to derive this in terms of y, which is like, in this case, we're not gonna do, you would derive the y as normal, but the x would be different, right? Because it would be 6y plus 6 dx over dy equals 12, because whatever you're deriving it in terms of, if we're deriving it d over dy here, the variables don't matter, but whatever variable you derive it in terms of, you have to keep consistent. So related rates is basically when you have two different functions going on, and one of them is affected to the other one. It's related, right? And you have to see why it happens. An example of this is for a certain rectangle, the length of one side is always 3 times the length of another side. If the shorter side is decreasing at a rate of 2 inches per minute, at what rate is the longer side decreasing? I'm going to get rid of part B, we'll look at that later. But what does this mean, right? First step when you're solving any related rates problem is, well, A, recognizing that it's a related rates problem. So we see that we have two sides that are related to each other, right? One side is always 3 times longer than the other side. When we're trying to find the rate that this is decreasing based on the rate that this is decreasing. So it's two things that are related, and you're looking at rates. You could assume it's related rates. So the first step in a related rates problem, once you understand that you're doing a related rates problem, is to write down all the information that you have. So we know that it's a rectangle, right? So let's draw a rectangle. Drawing is really helpful in related rates problems. So we'll draw a rectangle. When it says the length of one side is always 3 times the length of the other side. So we'll label one side S, the short side, and we'll label one side L, because it's long. And we'll say that L equals 3S, right? Because the long side is 3 times the length of the short side. It says the shorter side is decreasing at a rate of 2 inches per minute. So that means ds over dt equals -2. What is this, right? ds is the shorter side, it's the change in the shorter side. And then dt is the change in time, because we're measuring in minutes, right? So we're measuring the change in the shorter side over the change in time. This is a derivative, right? And since it's decreasing, it's -2. That's just written right here. It's asking that at what rate is the longer side decreasing. So, like, what does that mean in calculus terms? All that means is dl over dt, right? Change in the long side over change in time. So how could we get dl dt from this information that we have here? If we look here, we have an L function, and if we derive this in respect to t, in respect to time, right? If we derive the left side, we get dl over dt, right? There's the same thing as deriving y in respect to x, or x in respect to y, right? You're deriving this L in respect to t, so you get the 1, because L will turn into 1, and then times dl over dt, because they're different variables. And then, if we derive the right side of this, we get 3, and then same thing as with this L, we have to add a ds over dt. And then now that you have this, you know that ds over dt equals -2, right? We have it written over here on the left. So all we do is plug in -2 for our ds over dt. We get dl over dt equals 3 times -2, or -6. And can't forget the unit, inches per minute. And so that's it for this problem. It's like a little puzzle. You have to find out what you're looking for, and then derive it, and then solve it. So once again, all we did was write down the information that we had, found out what we were looking for, and then found out how we could get that information based on what we had. And so we had our L function, so looking for dl dt just meant that we had to derive this L function in respect to t. And question B says, at what rate is the enclosed area decreasing when the shorter side is 6 inches long and decreasing at a rate of 2 inches per minute? So again, let's write down all the information that we have. We know we have a rectangle, and we know that we have a short side, and we know that we have a long side. In this case, I'm just going to label L as 3s, because we already know that it's 3 times longer than the short side. What else do we know? We know that the shorter side is 6 inches long, pause, and we know that it is decreasing at a rate of 2 inches per minute, right? So we know that the shorter side equals 6, and ds over dt equals -2, right? It's the change in the side over the change in time is -2, because it's decreasing by 2. And what are we looking for? We're looking for the change in area over the change in time, right? dA over dt. To find what the area function is, it's a rectangle, so you have length times width, right? Or in this case, s times 3s, because those are the length and width values. And if you multiply those out, you just get 3s squared. So our area function is 3s squared. So to find dA over dt, what do we got to do? Go ahead, pause it now here, try to solve it out, and I'll go over it. I'll give y'all 3 seconds. You better pause it right now. Alright, cool. So to do this, you derive our a function, our area function that we have, with respect to time, because it's, again, measuring in minutes, right? So we have dA over dt equals, and then you will have to derive the right side, so you get 6s ds over dt, right? And then from here, you don't gotta do no calculus no more, because you have s and you have ds dt right over here, right? So you just plug it in. So you have dA over dt equals 6 times 6 times -2. Multiply this out, you get -72. Can't forget the unit. We're talking about area, so it's inches squared per minute. So that's it for this problem. We're going to look at a couple more, because I know this concept is complicated for a bunch of people. Okay, so up next we have another problem. It's another rectangle, and it's more area, but it's a little bit harder, but it's in the same ballpark, so we're going to give it a try. It says the width of a rectangle is increasing at a rate of 3 centimeters per minute, and its length is increasing at a rate of 4 centimeters per minute. At what rate is the area of the rectangle increasing when its width is 6 centimeters and its length is 7 centimeters? So, first step, write down everything that we have. It's a rectangle. Saw the word rectangle. I'm going to draw a rectangle. We have W and we have L. We have its length and we have its width, right? We know that the width is increasing at 3 centimeters per minute. So that means dW over dt, because minute time equals 3. We know that its length is increasing at 4 centimeters per minute. So we know that dL over dt equals 4. At what rate is the area of the rectangle increasing when its width is 6 and its length is 7? So this is telling us that the width is 6 and the length is 7. And we're looking for the area of the rectangle, the rate of the area of the rectangle. So we're looking for dA over dt. So just like before, we have our equation that area equals length times width. Same as before, but now we don't have, it's not easy because length isn't 3 width or anything. They're not like related to each other. It's just length and width, right? So if we're deriving this, it's 2 different things multiplied together. So this is going to be our product rule. Hopefully y'all know this by now. It's f prime g plus g prime f, right? Or the other way around, it does not matter at all. So let's label the f and the wg. I know it's all just letters, but we'll get to numbers eventually, I promise. So we have f prime g. So f prime is just going to be dl over dt, because it would be 1, and then you have to multiply it by dl dt. And then you have w, which is g, it stays the same because it's f prime g, plus f, you keep it the same, is l. G prime is dw over dt. This looks like a whole lot of letters, but look at this. dl dt, where's that at? That's right here. Okay, cool. W, where's W at? That's right here. Cool. L, where's L at? It's down here. dw dt, where's that at? It's right here, right? So we have all the information that we need to fill this out, and we're low-key done with all the hard stuff now, right? Now we just have to simplify it. dA over dt. We plug these in. dl over dt over here is 4 times W is 6 plus L is 7 times dw dt is 3. So dA over dt equals 24 plus 21, or 45, right? And we have to do the units. It's increasing, so it's positive, and it's counting in centimeters, and it's area, so it's centimeters squared per minute right here. So it's increasing at a rate of 45 centimeters squared per unit. So again, this concept really looks scarier than it is. You find what you're looking for, derive it, plug it in. I'll look at another one, but I'll let y'all solve it first, and then I'll go through it. So up next, we have another related rates problem. You guys should try to do this on your own. I'll give you a hint. It uses the Pythagorean theorem, and it's about a triangle. That's more about rectangles. This one's about a triangle. Yeah, so go ahead, pause it now, take your time, solve it, and then I'll go over it afterwards, see if you can check your answer. Okay, so hopefully by now y'all have tried it at least. Hopefully y'all got it right. So let's look at how to do this. I'm going to switch to a new tab because it's going to take a lot of space. So up first, what do we know? We know that there are two cars driving away from an intersection in perpendicular directions. Perpendicular means like this, right? Crossing. Because it's an intersection, you got cars coming up, cars going left, right? So if they're driving away from an intersection in perpendicular directions, one of them's going up and down, one of them's going left and right. So they're going to be driving like this. And you got your one car over here, because he been driving, boom, 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 right? You got your one car up here, driving this way. You got a crazy car, look like a platypus, right? So one's driving this way, one's driving this way, perpendicular from each other. What's next? The first car velocity is 7 meters per second, and the second car's velocity is 3 meters per second. Okay, so let's call this car A, and let's call this car B. The velocity is dA over dt. So that's going to be our first car. The velocity is 7 meters per second. And the velocity of the second car, dB over dt, is 3 meters per second. We know that the first car is 5 meters from the intersection, and the second car is 12 meters from the intersection. So this length here, length A, is 5, and length B is 12. So A equals 5, B equals 12. And what are we looking for? The rate of change of the distance between the cars at this instant. So if we connect these two cars here, we got ourselves a little triangle, right? Because one car's here, one car's here. The distance between them is going to be this value here. We're going to call it, for no reason at all, C. Okay? So for y'all that know triangles, y'all that know your Pythagorean theorem, you'll know that the equation for C is that C squared equals A squared plus B squared, right? So if we're just trying to find C on its own, C equals the square root of A squared plus B squared. Because you just square root both sides to give it the square root on C. And no, this does not mean that C equals A plus B, because it doesn't work like that. It's a square root. It's over all of it together, not A and B individually. So we're looking for the rate of change of the distance between them. So we're looking for dC over dt. Now, after all of this, we're done with setup, and we can start getting to the equation and finding what dC over dt is. So to do this, to find dC over dt, we have to derive our C function, because we're looking at dC over dt. T is minutes, it's time, same as usual. So to derive this function, dC over dt equals the square root of A squared plus B squared. We're deriving that. How do we do that? This is chain rule, because if y'all remember, square root of something is the same as something, in this case A squared plus B squared, to the power of 1/2. So if we derive this using the chain rule, we get 1/2. We keep the inside of the parentheses the same, power negative 1/2, and then we have to multiply it by the derivative of the inside. So in this case, it's times A squared is going to turn into 2A, and since it's implicit differentiation, we have to keep the dA over dt plus the derivative of B squared, which is 2B, and it's implicit again, so we have to put dB over dt as well. So now that you have this, you could plug everything in now, but I think it's a little bit easier to make this look less ugly. So I want to get rid of this negative 1/2. I think it looks terrible. So the negative means you put it on the denominator, and the 1/2 means it's square rooted. So this is the same as 1 over 2 square root A squared plus B squared. And we can keep the rest of it the same. It's not that bad. It's not that ugly. Okay, and now we can start plugging in numbers. So 1 over 2 square root. A is 5, so A squared is 25, plus B is 12, so B squared is 144, times 2 times A is 5, and then dA over dt is right here is 7, plus 2 times B is 12, and dB over dt is 3. Now let's start simplifying. This is algebra. We're done with calculus. We're done. So I'm gonna write this in red to make it a little bit clearer what we are working on. So if we have the inside of this 144 plus 25, you get 169, and the square root of that is 13. So we have 1 over 2 times 13 times, let's simplify all of this out. 2 times 5 is 10. 10 times 7 is 70. Plus 2 times 12 is 24. 24 times 3 is 72. So times is going to be 142. So we're left with 142 over 26. All I'm doing is multiplying this bottom here. And we can simplify this. We'll get 71 over 13. And can't forget the unit. What is the unit? They're driving away meters per second, right? 71 over 3 meters per second. So this is going to be it for a Pythagorean theorem type of problem. So it's the same concept as before, just with the triangle. So you find the equation that you're looking for, and you derive it, and you plug everything else in. This is going to be it for related rates. I definitely recommend going on Khan Academy and doing some more practice problems if you don't get it. But we're going to move